Ion, or are we looking at chromium, the metal? Ion. How do you know it's an ion? It's got a charge in the upper right-hand corner. That charge is a +2. Should I specify that information? Yes. Why do I specify it? You were not asked to memorize that ion. Okay. Group 1, group 2, nonmetals, zinc, cadmium, silver. I know that was fast. Should we try that again? Group 1, group 2, nonmetals, zinc, cadmium, silver. Those are the ones you need to have memorized. Where is chromium? Not there. Good answer. Which means you have to specify it. Okay, so we use Roman numerals, chromium 2. By writing chromium 2, it's implied already that it's an ion. You don't need to add the word ion, but it's usually nice to be extra clear. Okay, so let's take a look at one more. How about this one? Second column. The element, I heard someone say it. Sodium. Right? Is it an ion?
Yes.
How do you know? There's a charge written in the right-hand corner. Okay. Should I specify that charge?
No.
Why not? Group 1 metal. So I don't specify the charge. Okay. Remember we said the ion was optional. Okay. So we don't have to add the word ion, though sodium is a particular case where I would add the word ion. Because if I said I ate some sodium, okay, I could very well be dead, or I could have functioning muscles. Sodium ion is required for muscles to function appropriately. Sodium metal very quickly turns into hydrogen gas when it reacts with water in my body, generating enough heat to probably cause me to explode. Okay. That's a pretty significant difference, and that difference came down to a single electron. Maybe it's important to specify the word ion so that I know I'm not dying and exploding. Okay? So again, not critical as part of the name. Typically we'll ignore it because we tend to not name our ions, but that's what's happening. What happens when we move down to the anions? Okay. If it was just like the other one, I could say oxygen 2 ion, except a couple things come out of this. The Roman numeral specifies, you're not writing that by the way, don't. The Roman numeral specifies charge on cations. Is oxygen a cation? No. So I can't use the Roman numeral there. Okay. Should I have even suggested 2, be it negative or positive? Should I have even written a charge there? Why no? Oxygen's a nonmetal. We're required to know the charge on it. We're required to know it's -2. So the charge shouldn't get written there. Okay? But how do I know I'm referencing oxygen now? With the metals, we at least every once in a while dropped in the word or the Roman numerals. Okay? So to add extra information to this being an ion, we will change the suffix to ID as in dog, E. And we would end up with oxide. Because the suffix, the end of the name, is obviously YGEN. Okay? If anybody thinks that's obvious, get out. I don't think that's obvious. Okay? Why would we pick that as the end? What if I just gotten rid of the N? It would have been oxygeide. Ooh, that sounds awful. Okay. Maybe the EN. Oxygeide? Oxygeide? That sounds pretty weird. Let's get rid of the G. Oxygeide. That's even worse. Right? Let's get rid of the Y, G, E, and N, and I end up with oxide. Oh, that's not that bad. Let's call it oxide. Is it kind of that stupid? Yes. Yes, it is. Sometimes they're more obvious than others, but for the most part, you're chopping off some portion of the end of the name and hoping it sounds nice. Okay. If it doesn't sound nice, keep chopping off portions of the name. Kind of makes sense? SE is selenium. I'm not sure that's one you were required to memorize, so don't stress. Okay. But it's an ion. Okay. Should I specify the charge? No. Number one reason, it's not a metal. Number two reason, it's negatively charged. Okay. Our charges our negative charges are not specified in the name. Where is selenium? Well, it's a -2. I wonder if there was another element that had a -2 charge that we just looked at. Oxygen. Well, if I have something with a similar charge, they probably have similar chemical reactivity. I wonder if we have this table that organizes similar reactivities into, say, groups, families, or columns. Oh, look at that. Yeah, we do. Where's selenium? In the same column as oxygen. Right? So, what's the suffix in selenium? Seleniide? Seleniide? Selenide. Ooh, that sounds a lot nicer. Let's stick with that. And we get selenide. Okay? Kind of arbitrary, but that's what's happening. Just chop it off and put it in. Do you need to specify the ion with these? Again, not really. Even less so for the, what are they, anions instead of the cations, because the anions, we changed the ending already. By writing IDE, we've already implied it's an ion. So adding the word ion is saying, like, it's an ion. Okay. It's not really wrong, it's just kind of silly. Okay. After that, you get naming the polyatomic ions. Okay. Well, how do we name that first one? Okay, well, I see sulfur, and I see oxygen, and I see a 4, and I see a -2. Sulfur, oxygen, 4, -2 is a horrible name. Right? What do we end up naming it based off of? It becomes sulfate. What? What's the logic behind that? What's the logic behind what we name N? What is the name for the symbol N? What's the logic there? Why'd you call it nitrogen? You were told that was the answer. Guess what your polyatomic ion names are coming from. You are told the answer. Memorize them. Instead of now being 30 periodic elements that you have to memorize the name, symbol, and charge on, you now need to memorize some polyatomic ions too. If you watch the video, it's not all of them, it's 6 of them, maybe 7, because I can't ever remember. It's 7. You'll have to memorize 7 of them. So when you go through and do this part, what are you expected to do?
Look them up.
Look them up. That's it. Don't make it more difficult. Use the information you have. You got a textbook, look them up. Okay? Same deal for the ones underneath it, though there is a pattern with those. I don't really want to worry about the pattern because I don't think it's all that big of a deal. I will leave that to your instructor or you, or if you look carefully at the pink green sheet, different sheet, you can figure that out. What happens if I add hydrogen to sulfate? We become really creative and we call it hydrogen sulfate. What is the name for CO3? Carbonate. What happens if I add a hydrogen to carbonate? It becomes hydrogen carbonate. Again, super creative. That's all that's happening within those. Within the polyatomic ions, what you will notice is that for nearly every single one of the polyatomic ions, they will end in A or I, T, E. And I'm actually going to call attention more to the T. When we looked at our anions, what did we change the ending to? ID as in dog. If you see ID as in dog, you're looking at a single element. If you're looking at, say, sulfate, there's a T there. What does the T mean? Ternary. You're looking at a complex ion. Okay? With two glaring exceptions. Cyanide and hydroxide. Okay? Interestingly enough, I believe both cyanide and hydroxide are ones I tell you to memorize because they're kind of the exceptions to that trend. The video makes reference to some 8-ite thing, and I think I get snarky at that point. I'll get snarky again. The whole 8-ite, more oxygen, less oxygen is a load of crap. I mean, just memorize. Let's memorize this rule to remember that in these certain cases, 8 means more oxygens and 8 means less oxygens. But it's only in the cases when it's sulfate and sulfite, but not nitrate and nitrite. Why don't you just memorize sulfate and nitrate and their names, instead of memorizing a stupid rule to memorize it? You're memorizing it. Okay? So just literally just memorize these is the best way to do it. You will need their charges. You have to have those memorized. That then sets you up with the basics. The rest of the assignment then goes into kind of gory details. You're now being asked to compose simple ionic compounds. Okay? When we compose an ionic compound, we will end with what kind of a charge structure? Neutral. Which means if I start with sodium ion with a +1 charge, and a chloride ion with a -1 charge, what does my formula need to be? Na and Cl, how many sodiums, how many chlorides? One of each. Because that's when it neutralizes. Could we have done Na2Cl2? Doesn't that neutralize? Yeah. Okay. By that same token, I could have written Na 1 million, Cl 1 million. Okay. Which is easier? NaCl. Reduced numbers. Okay. So the rest of these are having you recognize how to get the charges to balance. So let's pick one more. Play a little game of Battleship. I'm going to call calcium nitride. Ding. Putting this together, I have calcium and nitrogen. The charge must come out to be 0. Calcium's a +2, nitride's a -3. Does that equal 0 when I add those up?
No.
So what has to happen? I need 3 calciums and I need 2 nitrogens to balance it out so that I now get an overall charge of 0. For those of you who are really good at math, that's cool. For those of you who aren't, this should look familiar. This should look exactly like what we talked about on Monday. That's because it is. The number of our cation times the charge on the cation plus the number of the anion times the charge on the anion must equal, I'll accept 0, but only partially. Neutral's on equal standing as 0.
The charge of that.
It's our overall charge. Which at this stage in the game, what is our overall charge? 0 or neutral. Okay? So you will find that you will likely have to go back to some kind of balancing out of those charges depending on the compounds. Your book mentions a crossover method. For those of you that have gone to the tutoring center, you may have seen or heard me yell at tutors like, why the hell are you talking about it like that? That makes no logical sense. Why are you doing that? Okay? That's because it doesn't make any logical sense, but it helps you get the answer right. Okay? Which, to a certain point, if you get the answer right consistently, I got to shut up. I won't, but I will try. Okay? So, the crossover method can work, but you have to watch out for it because there's cases where it kind of fails and gets in the way. I don't want to talk about it because it fails for me. So when it fails for me, I don't bring it up because I will then make you screw it up. This always works. Or those saying, well, I'll just do the crossover method because I'll never have to worry about this. This formula comes back to bite you again. Learn it now. Okay, then we got the rest of these. More. Oh, because you're like, oh, I didn't get enough practice. So here's more practice. You're like, okay, well, thank God. I can now move on to the next one. Okay, so now I have no extra guidelines. I'm expected to go through and just put the name together for these. Okay? Pick one. Yeah, that was a bad statement to make because I had to find it. There we go. Thank you. ZN3PO4. Okay. I want to name that compound. So what's the information that I know already? Okay. Zinc. I didn't hear phosphorus and oxygen being shouted out. This is a complex ion. It's a ternary ionic compound. As soon as we hit ternary ionics, you need to be looking up the complex ions. PO4 happens to be the formula for phosphate. Okay. What else needs to go into this name? The charge on what? Zinc. What is the charge on zinc? Wow, Mike is good at math. How did he come up with 2 so fast? You are required to memorize group 1, group 2, nonmetals, zinc, cadmium, silver. You're required to know that zinc is a 2, which means your name is zinc phosphate. It's not zinc 2-phosphate. By specifying that 2, you're supplying information, while technically correct, should be implied, which then means you're wrong. You only supply the Roman numeral when you aren't required to know it. So the name becomes zinc phosphate. Could we go through and prove that it was a +2? Yes, you can go through and do that formula thing to prove that out. Well, that's our name for that compound. What about the zinc 3? There's a 3 there, there's a 2 after the phosphate. What are those there for?
For how many?
For how many of each of those to do what? Balance the charge. Okay. When we're looking at our ionic compounds, we don't specify the amount of them. Which means I don't care what those numbers are as long as the charges balance out. Okay. Should we pick one that you have to know the charge on? Or you shouldn't know the charge on?
That's it.
The Cu-C2H2.
Okay. Oh, just a little bit lower. Do I want to do that one? Yeah, I will do that one. I'll do that one, and we'll do this one. Whoops. Whoops. Anybody notice any patterns common between those two green stars?
It's just rearranged.
I see a lot more carbons in the other one. I have twice the amount. What's happening? We're changing the amount of acetates. Okay, so which brings up an interesting point. So let's go through and do our bulk name. Cu is copper. C2H3O2. Acetate. How'd you know it was acetate? You were told it. You had to have it memorized. That is one of the ones I do expect you to memorize. You see it frequently. So as far as the names of these two compounds come down, they're both the same. This becomes a problem because are their formulas the same? No. So there has to be some extra information here. That extra information happens to be the charges. Okay? The charge goes to which element or which species, the copper or the acetate? It'll always go to the metal. The Roman numeral always goes to the metal, which is copper. So I need to specify the charge on copper in each of those compounds. How do I figure out what it is? Okay. We are required to know the charge on acetate. So if we broke this down, I have one copper, I don't know its charge, plus I have one acetate, I need to know its charge is -1. This must equal 0. How do I know it's 0? Upper right hand corner has nothing written. I now solve for x. What is x? 1. And that becomes copper 1 acetate. Make sense?
No, that's okay.
Okay, no. So let's look at the next one. This one, I have a little more space, so I'll write it all out. There's one copper in this formula. I don't know its charge. Plus, how many acetates? 2 acetates. What's the charge on acetate? -1. This must equal the overall charge. The overall charge is written in the upper right-hand corner. There is nothing there, so that must be a 0. I get x minus 2 equals 0. Yes?
So x equals 2.
Add 2 to both sides, and I get
X equals 2.
x equals 2. What did I say x was? Do not tell me 2. It's the charge on our copper. Where do I specify the charge in the name? Roman numeral right after the element it's referencing, and I get copper 2 acetate. Isn't that a lot of work? Yeah, that's a lot of work. Okay. How could I be expected to put all of that work on that sheet of paper? I don't know. I think it's dumb too. Okay. Get a separate sheet of paper. Write your work down there.
Would she want us to include our work, please?
I cannot ask what another instructor wants of you, or answer that, unfortunately.
Cool.
Okay. The last thing that I'll mention here, because the textbook mentions it briefly, I don't have to call this copper 1 acetate and copper 2 acetate. I could call it cuprous and cupric acetates. It's the Latin origins of these. Your textbook mentions it, confuses the hell out of me. I have no idea which one's which. If you want to learn to do the Latin roots for those, by all means have fun, go at it. I'm not going to test you on it. Okay? This is what you're expected to know. Make sense? How many of the categories did we just learn how to name? 2. Binary ionic and ternary ionic. The next one is the molecular compounds. These ones, you just write what it tells you. They're kind of nice in that respect. CO2. What is C? What is O? O is oxygen, but it's showing up at the end. We have to make sure that we know it's part of a compound, so it becomes oxide. It says there's 2 carbons, so that's it. Isn't that sweet? You just write down what the elements are. And then you say how many there are. So let's see if I can find a harder one there. Yeah, that's what I was looking at. P205. What is P?
Phosphorus.
Phosphorus. Okay, what if it was PO4?
Phosphate.
If it's PO4, a couple people are falling into a trap and saying it was phosphate. So let me write that down so we can see it. PO4. You're telling me it's phosphate. Why are you saying no?
Because this is P2.
Well, no, I said a new compound. If it was PO4, and some people are telling me phosphate, I'm saying you're wrong. Put the -2, now it's phosphate. If it's not charged, it's not phosphate.
Got it.
Okay? If it's in a compound, then it's by definition charged. Okay? So we have to be careful with some of these. So, wow, I wrote phosphorus really big. Dang, I'm going to have to move on to the next line. Name for O. Oxygen, which becomes oxide. How many phosphorus are there? 2, so it becomes diphosphorus. How many oxygens? 5, so it's... Oh, I had to do this one. Brick. Anyone help me out? Pentaoxide or pentaoxide? Yeah, that's exactly my confusion. You think it's PA?
You put it in parentheses last time.
Yeah, because I don't remember. Okay. You asked me, it's a spelling thing. Multiple choice. Don't worry about it. Okay? Make sense? What if we move down to the bottom ones? Let's make those a little bit more challenging, because I think they've got a little bit more challenging ones down there. Whoa. Triiodine non-fluoride. Triiodine. I. The tri is 3, but where does the 3 go? Goes after as a subscript. Non-fluoride. What element is not fluoride? It was just fluoride? I said fluoride, fluoride. Just fluoride. Sorry, shouldn't have tried. Which would be F. What is nana? 9. And I don't mean that in the German sense. I3F9, and we have our formula. If you don't know German, don't worry about it. Okay? It looks like I'm turning this whole lecture into nomenclature. Oh well. I'm fine with that. Actually, I'm not really. I don't like nomenclature. But. Okay. Binary acids, ternary acids. These ones are relatively short. Right? Big characteristics. Acids. How do we know we have an acid? AQ. And it starts with an H. Those are the 2 rules that you have to work with. Are all acids identified this way? No, not by a long shot, but we were trying to simplify things. So you need to find that H, you need to find the AQ, and you know you have an acid. If you have an acid, guess what your name ends with? Easier. It ends with acid. Okay. So what would the root of our name be? Okay. Fluorine. Oh, but it's the end, so we can call it fluoride. Oh, but it's an acid, so I can't call it fluoride. I'll call it fluoric acid. Because it is a binary acid, and because it is a binary acid alone, I will also specify that it has hydrogen by saying hydrofluoric acid. So the formula for hydrosulfuric acid would be H, good place to start, good place to end. Good place to end.
AQ.
AQ. What's in the middle? S. S for our sulfur. Is this the correct formula for hydrosulfuric acid? Nope. What is the charge on sulfur? A -2. How do you know that? You memorized it. Hydrogen is a +1. We have to have a neutral structure. That's not neutral. I need 2 hydrogens. H2S. AQ. And I now have hydrosulfuric acid.
And the answer.
Okay? Sure you get confused? Good. Me too. H2SO4. Okay, so I heard hydro. We have acid at the end. This is sulfate. Okay, so hydrosulfate. Okay, but sulfate is the ending that needs to change because we're an acid. What does the 8 become? I ate too much, so I became sick. And this one gets weird. We add the UR in there because it sounds nicer than sulfic. And we get hydrosulfuric acid. Anybody want to be like, I don't like that? Why, Nick? But that's accounted for in the name sulfuric because it was sulfate. So sulfate does include, or is required to have, those 4 oxygens.
You could take out the hydro.
You all took careful notes, right?
Oh, is it dihydro?
Did you all take careful notes? That last question that we just looked at, what was its name? Hydrosulfuric acid, right? Isn't that what you wrote down? What did we just write down here? Ooh, are those the same thing? No. So we have to change the name. Remember what I said? And I did this fast. I know, I did it intentionally fast. I said, when do we include the hydro? In binary. Binary means how many elements? 2. How many elements are here? Not 2, which means can't have the hydro. It's sulfuric acid. So when you have a ternary acid, you do not use hydro. That whole I ate too much and became sick is perfectly valid. You got to use that one. The other one is something about I and us. It becomes us when we sit together. Like I and you make us. Mnemonic devices are not my thing. Okay? So how would we apply that one? How about the name for the one right next door? Should we use hydro? No, because it's a ternary acid. We can end in the acid. What is the name for SO3? Sulfite. Here's that ite issue. Okay. Well, ite, when you sit together, becomes us. And again, sulfur is a nasty one. We add that UR in there. Just because if it was too methodical, everybody would get it right. Don't blame me. I didn't do it. Okay? We good? Easy. Now you just got to do it for the other 110 questions. Okay? And because you've had such good practice at this, and we're now like awesome, we're like, well, thank goodness we don't have to do any more. That's the last page. Within that last page, what's the added thing that they did to mess with you? They mixed up all the different names. So it's now you're not naming just one class. So it can be helpful to go through and label what class it is before you start using your rules to name it. Okay? And because I always forget to mention it in lab, so I wouldn't be surprised if somebody else forgets to mention it in lab. Ammonia and chlorine. You're going to have a really hard time naming those. What element is or amon? Or, yeah, what else? What? Ammonia is NH3. There is no origin there. Don't try and make one. Okay? It's a common name given to it, much like my name is Mike. Okay? Chlorine would just be Cl, but some elements have a special characteristic where they need to be partnered with another one. We kind of talked about this with hydrogen and oxygen. Guess what? Chlorine's the same deal. So when we refer to chlorine, it needs to be Cl2. The rest of them follow the same patterns described, I believe, so you should be okay. What do you guys think? Confusing now, but if you go through and do this packet, please do it before the exam. You will find the nomenclature questions on the exam easy and straightforward. There is, so this is another interesting question, because I notice students do that with this one too. There is no answer key posted for this. I'm not going to post it. I don't post answer keys. However, if I go into Google and type nickel 2 perchlorate, guess what it tells me? The answer. Okay, it'll give you the formula. Okay. Don't use Google to write down your answers. Use Google to check your answers. Okay? Questions about any of that? Okay, that kind of bothers me, so I'm going to have to talk for at least another 5 more minutes because we literally did nothing from the lecture. Which means I might, well, no, because the first part I actually like. So we talked about qualitative and quantitative already. Qualitative was
What you see.
kind of what you see, the pretty pictures. Okay, quantitative, what you measure, numerical amounts. Okay. Physical and chemical properties. Okay, you might go, didn't we do a lab on this? Yeah. This is that out of sequence thing. Okay, physical properties are observable characteristics that do not alter the elemental composition. Meaning, when I look at a physical thing and say it changes, the bonds or the formula for said compound does not change. Okay? Why would I put that later in my presentation than start the class with that? Remember back day 1, how many of you knew what a formula was? Oh, that's right, you didn't. It's kind of a dumb lab to start with. Okay? Because you don't have the basis for what elemental compositions are. And now that you have that, you can start to use that information. Chemical properties. Okay? A chemical property means that when we go through and put it in a different environment or near another chemical, bonds change location. Okay? When I mix hydrogen with oxygen and give them enough energy, they become H2O. They became a new compound. I went from the gas to the liquid. Okay? Can't say gas to liquid, that the compounds actually changed. The bonds changed. Okay? So in our chemical and physical changes, your physical changes are looking at things that don't change the composition of the compound. Oh, well, that's obvious. Thanks, Mike. Okay? It's not obvious. It can be a bit difficult to nail down. Okay? But you're looking at a process where the compound does not change its structure or its composition. The chemical changes, you will change the composition. Okay? A new substance is formed. Okay? Evidence for chemical reactions. Okay? Your textbook lists them as 4. I list them as really just 3. 1 and 2, I think, are the same thing. It's a change in phase. Okay? Going from typically forming a gas, okay, that is typically considered a chemical change. So I put a pot of water on the stove and I turn on the heat. What happens to the pot of water? It boils, and that boil is that bubble is gaseous water. Is that a chemical change or a physical change? That's physical. Okay? Nothing is happening to the chemical bonds that make up water. Okay? It is changing its phase. So when we're thinking about this change in phase, what we need to do is say we are not adding or removing heat. If I add heat, I'm supplying the energy to change phase. If I remove heat, I'm taking the energy away to force the phase change. That is me physically doing something. Okay? So remove heat from it. I mix 2 liquids together and they start blowing up, bubbling. Let's be nice. It bubbles. Okay? I didn't supply any heat. I just mixed those things. How did I go from a liquid to a gas? Well, liquid to gas requires energy. Where did that energy come from? The chemicals, chemical change. Okay? Same thing happens with the solids, just in the reverse. Okay? These can be referred to as solids, crystals, or precipitate. Okay? Permanent color changes. Okay? A permanent color change. Here we're seeing a yellow form, presumably from two clear liquids. Okay? So we got a solid, because light's not passing through that, and we've got a color. Both of those are signals of a chemical change. Cake frosting, right? Anybody used cake frosting before? Okay, you can buy it white, right? But I want it blue. How do I make it blue? I add food coloring. Is that chemical or physical? That is physical. I'm not changing the chemical nature of either of those substances. I'm just mixing them together. I'm getting a dilution. Is that color change permanent?
No, because you could add another color.
Can you reverse? That blue is permanently there. You can't get rid of it. You can dilute it by adding more white, but it is permanently now blue. So the whole reversibility concept doesn't quite match and work perfectly with physical and chemical either. Okay? We have to have a deeper understanding of what's happening at the chemical level, okay, the chemical structures. The last one, energy changes. Excuse me. A release of heat is exothermic. Okay? This is typically signified by a negative energy if you were to do a calculation. Okay? Absorption of heat is an endothermic reaction. This is referred to as a positive energy. Okay? Light emission. Is light a form of energy? Yes. So if I run a reaction and I see light, what does that mean? Energy is being produced, but from where? If I just take a solid and a liquid and I put them near each other, there's no light. Okay? But when I mix them, all of a sudden there's light. Where'd the energy come from to make that light? The chemicals in the solution, doing a chemical reaction. So it's a question of where are those observables coming from? Are they things that I have put into it, or are they things that the chemicals did on their own? Okay? There's plenty of gray areas and plenty of difficulty. For those of you that watched the review, chemical and physical changes are a complete spectrum. Okay? And I've gotten into debates with people over this. Okay? We try to teach it as black and white, because if it's black and white, it's either right or wrong. It's easy. It's not easy. There's lots of gray areas. The big gray area from the video, salt dissolving. Okay? We've got dissolving sugar and dissolving salt, and this is what we'll end on, I promise. When we dissolve sugar, what do we start? When do we end? Okay, good. I was like, oh, we ended at 2. What's going on? Dissolving sugar. Sugar is a... Don't tell me sugar's a sugar. A solid. Give me more.
Crystal.
Crystal. Give me more. It's a white solid. Thank you. Dissolving sugar, we're assuming we dissolve it in water. Water's a clear liquid. Dissolving salt. Describe salt. It's a white solid. I take a white solid, I add it to a clear liquid. What happens? It all dissolves, I end up with a clear solution. One of them tastes sugary and one of them tastes salty. Okay? Dissolving sugar, chemical or physical? Physical. Dissolving salt. Chemical. Okay? Why? This comes down to what is happening at the chemical level. And how would you know that? That is insanely difficult for you to know until you've studied it enough. When we dissolve sugar in water, nothing happens to the water, nothing happens to the sugar. Okay? When we dissolve salt in water, what happens? Salt is sodium and chloride. When we add it to water, what happens? They separate into sodium ion and chloride ion. I no longer have salt. I have 2 ions. I have broken a chemical bond. That is by definition a chemical change. Is that process reversible? Yes. Which would suggest it's a physical change. Yeah. Okay. This is why we're looking at a spectrum. Some things very clearly fall as a chemical, some things very clearly fall as a physical. The way we know that difference is by studying these closely enough to recognize that differential. Which means Not something I typically ask because you don't have the chemistry knowledge yet to really nail those down. Okay? Thank you. I apologize for talking too long.